All right, so we'll talk about the test and about the homework and a little bit about band limited channels today. So let me go ahead and get things started here. Um, let's see, where's my Okay, so let's start with the test preview. So the test will be next Tuesday. Dr. Morrow will be proctoring for us this time, and but otherwise, pretty much the same process as before. So and I so uh, let's step back and look at the big picture here a little bit. Um, I observed that from the first test we had kind of a bifurcation. We had several of y'all did really well, and some of y'all struggled a little bit, right? So um, I think I'll do a combination of two things to make sure that everyone's able to be successful in this course and adapt. In the end, a grade reflects your mastery of the material that you're responsible for in this particular course, right? So I'm less concerned about what you know in February than what you walk away knowing in May, right? So therefore, I will um, uh, basically the final can help you a lot. I haven't decided exactly how I'm going to implement this, but if you had trouble on the first test but show continued improvement, then I will give much more weighting towards the end. um, I understand that things happen, and I don't want to be punitive if someone kind of blows the final because they've got a bunch of other finals that they're struggling with and that type of thing. So conversely, I'm not going to overweight the final if you happen to blow it. Um, so if you did really well on the first test and do less well on the midterm or the final, then they'll get averaged as normal. But if you show continual improvement, I will recognize that. Okay, so again, I haven't nailed down the exact mechanism I'm doing that with. I know sometimes professors drop the lowest grade or something like that, but or they set it up so that the final can only help and not lower your grade. So I'll figure that out, but I want to encourage you that sometimes it's a little hard adjusting to a new professor and a new type of learning situation. So um now so hopefully everyone can continue to improve throughout the semester. So additionally, I now as we get close to midterms and look towards the second half of the semester, I'm going to try to do a couple of things. One is um, figure out either a project or a lab or something like that. It's a little difficult me not being there on site and not being able to set up a lab full of computers with some software that would be relevant to this class or something like that and stuff. So but I'll try to do something like that. If not a lab, then we'll do some sort of project, and that might be reading some papers and reporting on them or something like that, like research papers. The other thing I might do, and as an offering of extra credit, as you know, as I've been saying along this class, there's a lot that is that we're skipping. We're trying to figure out how to teach this course with a reasonable level of depth, but still covering a lot of material at the same time. So that's challenging to do in one semester. So we're skipping over a lot of topics that are interesting in communication systems, and we're kind of going this deep instead of that deep on some other topics. So if you after the midterm, if you feel that you are still in need of some extra credit, then I will set you up with an opportunity to study one of these topics either a little deeper, or study one of the topics that we haven't done as more of a like an independent study project, and you do some problems, or write a report on that or something like that. So we'll see after the midterm how much that is really needed. Again, as a practicing engineer, I'm more focused on making sure that you guys come out of this class with useful knowledge that you can apply in the real world. I know grades are important, and so I want to help you with that. But my main goal is to help you leave this class with a practical set of knowledge that you can use in your career. So, all right. So, enough of that. That's just kind of a preview. So let's get back to the test preview. So the exam will be cumulative, and this helps me meet that kind of first goal of assessing you as you improve your knowledge of the course. So, but I will emphasize the receiver design and analysis that we've been focusing on lately. And also, we did have a few problems that had particular troubles with, and so I'm going to emphasize those. One of these was this Shannon-Hartley capacity theorem, and we didn't prove this theorem. We haven't worked with it a lot, but it's kind of foundational to communications, and so as you go through the course, theorem should just kind of become more intuitive to you as you work with it. But this says the capacity in bits per second is equal to the bandwidth times the log base 2 of 1 plus the signal power over the noise power, or the signal to noise ratio right there. Now, that's not exactly accurate. It doesn't equal that. It represents the upper bound. So this is as best as you can get. You might have to work really, really hard at getting the C that this predicts, right? So after this, Shannon came up with this in like 48 or 1948, something like that. So we've been working on this for 60 some odd years, right? No, more than that. Almost 80 years, right? So and we're getting closer and closer, but and generally the way that's done is through error control coding, which we'll touch on in the second half of the course. And but trading off when we have a fixed amount of bandwidth, if we use more signal or we somehow reduce the noise, then we're able to use MRE type of communications. It's maybe a term I haven't used enough, but it's the idea that we use these multiple constellation points, and we use more symbols. In other words, we're using a higher K, right? So we take a certain number of bits and encode those into one of a symbol set, right? So as that number of bits increases, then that symbol set size, M, gets larger, right? With this relationship of K is equal to log base 2 of M. And so if we have a higher signal power, then our constellation size can grow, and the extent of the constellation can grow because we're using more power, right? It's a higher level of amplitude, and the bandwidth is really affecting our symbol rate. So if we're a fixed bandwidth, then we're going to end up constrained to a limit on our symbol rate. But if we can map more bits to a symbol set, then we can accomplish a higher bit rate. So conversely, we can, if we can somehow reduce the noise, then we can, even if our signal power is constant, we can kind of fill in the constellation with more and more points. Yes, they're more closely spaced that way. We might go from a 16 QAM to a 64 QAM or to 1024 QAM. And each time those points are getting closer together. But if we reduce our noise, that's going to be okay. We're going to be able to distinguish one constellation point from another. If we can't really do anything with the SNR, then we use more bandwidth. All of these things are available to us as communications engineers to get more capacity out of the system. So we also talked about entropy, didn't go into a lot of depth of it, but if you're in an interview or something like that and someone asks you this, it'd be good to have some sort of understanding of what entropy is from an information theory perspective. It is also very important in AI. And if you think that you're going to go through your career and never need to use machine learning or AI, or conversely, never need to use communications theory, you're probably in for a surprise. Just like many hardware systems are now software defined, and even electrical engineers need to have a firm grasp of software development. Many systems have communications in them somewhere, and in the future we'll have more and more systems that have some level of AI. So entropy is also used in machine learning and training neural nets with a criteria called cross entropy. So entropy of a random variable in the context of information theory is the average level of information or surprise in the events or outcomes, right? So it's related to the probability of the random variable. A low probability event is actually surprising, right? So if it's a high probability, well, it's probably going to happen. It's not surprising, right? And so high probability doesn't have a lot of information associated with it. A low probability event is surprising, and therefore it's conveying a lot of information when it happens. So the low probability has a high amount of information and stuff. So we didn't introduce this formula earlier, and I'm not necessarily going to ask you the formula on the test, but so you understand that H of X is the measure, the symbol we often use for entropy in an information theory context. And so it's related to this negative log base 2 of the probability of X. So in a sense, the expected value of that. Sometimes you don't see someone formally carrying along that expected value, and they'll just kind of say h of x is equal to minus log base 2 of p of x. And actually, Shannon uses the log base 2, whereas some other authors use log base 10 and that type of thing. So, but this is a general idea, and so as the probability gets higher, your logarithm would normally increase, but we're negating it here. So so that's how the entropy is measured there. So all right, FSK signals. We also had a difficult time with this, and I think because we didn't have really a homework assignment on it and stuff. And we only covered it in one lecture, but it is an important modulation scheme. It's used in IoT devices and occasionally and that type of thing. So and it's also used in wireline communications quite a bit, not necessarily wireless. It is used in wireless. So FSK symbols, you remember, they are, let's say a binary FSK will in one symbol transmit one frequency, and for the other symbol, it will transmit another frequency. You can scale this up to more. You can go to 4 FSK symbols, and you're just transmitting the information on 4 different frequencies. And so your receiver just needs to measure, where is that energy coming from? What is the frequency in which that the transmission is presently, right? And maps that to a symbol, which then you can map to bits. So that kind of begs the question of how fast can we send symbols and still be able to discern what frequency is what at the end. If you think this through kind of heuristically, remember your Fourier transform theory. And I know sometimes in your first course on Fourier transforms, you tend to get a little focused on equations and that type of thing and solving problems. But there are some big concepts that you should take away from all these lessons and stuff on Fourier. And that is basically, if something's moving really fast in a time domain, then it's going to spread out in the frequency domain, right? So if you have a steep slope in the time domain, like a square pulse, right? So you probably learned that a rectangular pulse in a time domain has if you do a Fourier series expansion, it's going to have an infinite number of odd harmonics at progressively lower amplitudes, but there's an infinite number of them to resolve a perfect square wave, right? So that's kind of implying that it's taking more and more bandwidth. So anytime you see steep things or things that are changing fast in the time domain, your thought should go to wider and wider bandwidths. So if we're trying to cram a lot of data through this channel, and we're sending lots of samples, well, that's changing rapidly, right? So that's going to take up some bandwidth. Well, we're trying to encode these signals based upon what frequency they are. So there has to be some, enough separation in the symbol set that we can distinguish these things, right? So that we did a little quick derivation. At the end, what's important is this formula delta F min is equal to 1 over 2 T, right? T is a period at which you are sending the symbols, right? And keep straight the difference between rate and period, right? The reciprocal relationships. Period is time, like some number of seconds, whereas rate is something per second, right? The symbol rate would be the number of symbols per second that you're sending, right? So they're just reciprocals of each other. But delta min here is equal to 1 over 2t. That means that your symbol sets cannot be spaced closer than delta min, or you won't be able to resolve them accurately, consistently. So, okay. And at this point, the peaks of the sync-X behavior, or the inner product of the two symbols, this is how we derived it. And so the peaks are going to lie at the nulls of the other symbols. And that kind of a repeating theme. And in fact, if we get to it, we'll see that in our band limited communications today. So M-ary modulation allows us to encode multiple bits per symbol sent, right? As I mentioned at the beginning of this review, this is K is equal to log base 2 of M. When K is greater than 1, then we are using the available bandwidth. Okay, should more efficiently, right? So from Fourier relationships, we understand that fast-moving things take more bandwidth. By encoding multiple bits per symbol, we can reduce the needed symbol rate to send a particular bit rate, right? So we're wanting to send the bits. The bits are our information. But if we can encode those into symbols more efficiently, then the bandwidth of the channel is what's limiting our symbol rate. So we have this K is equal to log base 2 of M option to improve our bit rate even with a finite bandwidth. So when we go to M-ary modulation, and if we go to higher and higher M's, then we're more and more efficiently using the bandwidth that we have, right? So let's see. So according to Shannon-Hartley theorem, this comes at a cost of either increased signal power, decreased noise, right? That's at this equation up here. A lot of times we just call it the Shannon capacity theorem. Technically, we like to give credit to Hartley also. So he kind of predated a little bit, but I guess we'll skip over the history lesson right now. So we can see that when we consider that as K increases, the number of symbols increases. If we keep the same spacing, which translates into the same noise immunity, that distance D between our symbols, then we have to increase the outer dimensions of the constellation. This means more power. We're increasing the extent of the constellation. So it's more amplitude and therefore more power or more energy to transmit and ultimately receive. By the way, the signal to noise ratio, the signal power is at the receiver, right? So you transmit a certain amount of power and you're going to lose power along the way. But this is the signal power at the receiver. So if we keep the outer dimensions constant, then the spacing has to reduce to accommodate the additional symbols. This squeezing, or the symbols are all getting closer and closer together. This reduces our noise immunity, and therefore we need somehow to reduce the amount of noise. Right? So, all right, then using a Q function to calculate probability of error in a binary modulation system. We observe error we observe an error whenever the noise sample or the noise energy or the sample from that random process that we call noise, right? When that sample is large enough to push the received signal, remember it's additive, so it adds to that received signal. additive white Gaussian noise, right? And it can push the receive signal into a neighboring decision area. We and that's going to be flagged as an error, right? We integrate the Gaussian PDF because it's additive white Gaussian noise, AWGN. We integrate the Gaussian PDF for the portion of it that lies within the wrong decision area. So since the noise is zero mean itself, right? The mean of this Gaussian equation that we're integrating is the true symbol location, right? Part of that constellation. And mostly we've looked at, binary type things because that's a little simpler, but we've looked at them where they're antipodal. We've looked at them as their quadrature, and we've now in the homework assignment, we've looked at on-off keying. So 3 different approaches at this binary modulation. So in each of those cases, there's 2 symbol locations, ideal symbol locations. Those ideals are then, there's an additive Gaussian noise process superimposed on top of that. Where those tails leak into the wrong decision area across that threshold, that is going to represent an error condition. So we're integrating that region. Since it's binary, that tends to be from that threshold line, the decision boundary, out to infinity or negative infinity, depending upon the case that you're considering, right? So, let's see, since the noise is zero mean, the mean of the Gaussian is a true symbol location in the constellation. The error region is in the decision boundary to infinity on the other side. These are your integration limits, okay? So the Q function arises when integrating the Gaussian. And once we've done it, we rarely have to do it again. To integrate the Gaussian function, we just need to fit the problem into this, Q function relationship. And so now our probability of a bit error here, or symbol error, is this Q function where the argument is the square root of the distance between the constellation points squared divided by 2 times n naught, right? And so this distance becomes important, right? And that's related to the amplitude, which is related to the energy, and also this correlation, cross-correlation coefficient that we define here. And we note that they can often be determined by inspection, where -1, 0, and 1 are special cases, right? So -1 is an antipodal type of situation, 0 is a quadrature type situation. And so you can just see those by inspection. 1 means that they're perfectly correlated. So, all right. So,
Professor?
Yes.
Oh, we have a question?
Yeah.
Can you explain how you can figure out the cross correlation by inspection?
Yes.
Did you get that?
So, an example of how to determine cross correlation by inspection. So that is what I was just mentioning. If it's quadrature, then kind of by definition, they are going to have 0 cross correlation, right? So if you run through that inner product and sum it up, you will see that sum goes to 0, right? The integral from -infinity to infinity of one symbol times the other symbol. So if if one is on the imaginary axis and the other's on the real axis, then really your symbol is on the real axis, it's going to have some energy comma zero, right? And your or plus I 0 J 0, right? And on the other side, on the one on the imaginary axis, it's going to be 0, the real part's 0 plus J times some function over time, right? So when you multiply those out and integrate, you're going to end up with 0, right? So uh, uh, the other example, the other easy example is when they're antipodal, and there they have the same shape, the same amplitude, except a negative sign, right? So, that could be a negative sign in the coefficient, but since we are typically dealing with like cosinusoidal type signals, it could also manifest itself as a pi radians phase shift in the cosine or exponential, e to the j pi type of relationship. So either way, they're opposite each other, but they're the same. So if you integrated those over time, over this signal over time, and you're multiplying those together, they're the same. And so they're going to integrate to 1, except they're not exactly the same. There's a minus sign involved, right? So if they're equal but opposite sign, then they're would otherwise perfectly correlated except for that minus sign. So you end up with the -1. Okay. So all right, I hope that makes sense. If they're the exact same signal, then they're going to correlate to 1. That's not as interesting to us in communication systems, but and your the other values will lie somewhere in between plus and -1, right? All right, so equal probable signals make calculating decision boundaries simple. Well, it's all simple is always relative, right? But simpler since we can use the maximum likelihood receiver instead of the MAP, maximum a posteriori probability receiver. That's even hard to say, much less hard to build, right? So we can now use the graphical rule that we've talked about a few times by plotting the signal vectors in a constellation, right? So we've been recognizing that the signals themselves, the symbols, are some function of time. We haven't really delved into those until the latter half of this lecture, and which you may not get to, but we know that those have some tendency over time with some basis functions creation. We can map those into constellation points as vectors, right? So I say they're constellation points are really the endpoint of the associated vector that represents that symbol. Okay, so we plot those in our constellation. We draw connecting lines between all the nearest constellations, all the nearest neighbors. Then we draw perpendicular lines that bisect those connecting lines. Those lines end up being our decision area boundaries, right? And somewhere they will join, possibly, or they might be parallel to each other or something like that, right? So, but if you have a more complex or arbitrary constellation, then yeah, they're going to kind of join in some vertices and outline a set of decision area boundaries. So that really only applies that simply when you're dealing with that maximum likelihood receiver. When it's not equal probable symbols, then we need to account for this bias term. And that recognizes that some symbols are more probable to be sent than others in this case, and enlarges the corresponding decision area to account for that likelihood. So, and that's this term right here. Okay, so then finally we've started talking about this correlation receiver and a match for receiver producing identical results at the sampling instant when the decision is made, right? So where NT, where T is the symbol pulse length, right? And so we're going to send pulses one after another, and we're going to integrate or through this correlation process, or our filter is going to do that for us, right? A filter convolves the input signal with its impulse response, right? H of T. And so the output of a filter, which I hope you looked at some point last year in your signals and systems course, that if you take the signal and you run it through some filter that has a particular impulse response, it is convolving those together, right? And so convolution is another type of integral, and we looked at comparing correlation to convolution in the last class, right? So our conclusion is that both of these receivers, under will produce identical results at that sampling instance, but not in between, right? We don't really care in between, but we have to understand that they are produce equivalent optimal results, but do so in a different manner and approach. So, all right. So, we talk about things kind of generically, and my Zoom is going to